Welcome to all of you to the latest installment of the SLAC Public Lectures. We're very glad to present tonight a lecture by Yijin Liu from the SLAC synchrotron radiation source on the subject of the science of batteries and how we're going to learn how batteries operate and how they're improved. Now, Yijin is a graduate of the prestigious University of Science and Technology in Hefei, China. And that connection is an interesting story. The founding director of SLAC, Wolfgang Panofsky, actually personally went to Beijing in the 80s, in the Deng Xiaoping period, to help China set up the first large particle accelerator in China, the BEPC. And that initiated a program in China, both of particle physics and X-ray research based on synchrotron radiation. Over the years, actually, SLAC has benefited by having many of the star students in that program come to SLAC and take a major role in our accelerator activities. And Yijin is one of the latest people to come through that route. He has his degree, as I said, from the University of Science and Technology in 2009. He then went to Beijing to work on the X-ray program of the BEPS accelerator. And in 2012, he came to SLAC as a postdoc. He's an expert in imaging with soft X-rays. This is a regime that allows you to look at micron-sized objects and basically watch them evolve, these tiny things, in real time, both biological machines and interesting chemical machines of the kind that you're going to hear about tonight. And Yijin is one of the big experts in that kind of imaging. In 2016, he won the Spicer Young Investigator Award, which is an important award for this kind of X-ray science. And now he's a staff scientist here at SLAC. So let me now turn it over to Yijin, and you'll hear about how we look at batteries on all sizes and how we're going to make them better in the future. Okay, please take it over. Thank you very much.
Okay, thank you, Michael, for the very kind introduction, and for the. I want to also take this opportunity to thank all the committees for the invitation to present my work to the public through this SLAC public lecture. And I also want to thank all this audience who joined us this evening. And we are in a very difficult time, and in part because there are too many Zoom meetings for each one of us. But yet, you guys show up to this webinar, and that shows how much you like battery science. And before we talk about the batteries, let me again reiterate a little bit about myself. As Michael said, I came from China. I did my undergrad study at the University of Science and Technology of China. Then I went to Beijing for my PhD degree in the Institute of High Energy Physics in Beijing. And after that, I came to SSRL, I came to Stanford and SLAC, and I have been here ever since. Now, these universities I went to, they are apparently very different. However, there's one thing they have in common. That is this large-scale X-ray facilities. In Hefei, we have this National Synchrotron Radiation Laboratory. In Beijing, we have BSI, Beijing Synchrotron. And at SLAC, we have two. We have SSRL and LCIS. That makes it very attractive. So what are these large-scale X-ray facilities? If you zoom in, if you go inside one of these buildings, you will see that scientists are playing with these highly complicated and very advanced instruments for doing research in different research fields. And they are not just complicated. And the beauty of this is that they are very broadly applicable. So throughout my career associated with these X-ray facilities, I was given the opportunity to participate in research projects ranging from oil industry all the way to renewable energies. And you can imagine that when I was presented with this opportunity, I was like a kid in a candy shop, and my sugar high never failed. So I stay here ever since I was get into this business. Now, coming back to the topic on the research on energy science, I would like to refer people to this very nice perspective article written by Professors Steve Chu and Aaron Maganda of Stanford. So in this article, they talk about the opportunities and challenges of the our energy future. This is a very nice article. People should read it. In this article, there's one figure that caught my eye. And you can see from this plot, the horizontal axis is the time. The vertical axis is the percentage of the source of energy that is used in the United States. And you can see that nearly 200 years ago, people were burning wood. And after that, we found out that the coal is more efficient than wood, so we use coal to replace the wood. And then we find out that we can utilize the gas and oil to replace the coal. And now we are going into a time where there are many players in our energy landscape. So this plot actually tells me a few things. Number one, we are always looking for a more efficient and more sustainable energy source. And number two, it takes something like 50 years to have this transition happen. And finally, we are now in the time there are so many players, and we need to really carefully look into each of these puzzle pieces in order to make a very nice contribution to our energy landscape. Now, regardless of where you get the energy from, in order to effectively utilize the energy, we need something to store the energy. This is the energy storage technique. And lithium-ion battery is one of the most successful energy storage approaches that have been commercialized. And you can see there are many applications of lithium-ion battery in many different fields. For example, nowadays, everybody is walking around with a cell phone in your pocket. This is working because inside a cell phone, you have a small piece of battery that has energy that can be utilized to power this device. And there is a growing interest in electric vehicles, which we will talk about in the later part of this presentation. Now, if we go to even larger scale, you look at the renewable energy generation. The renewable energy generation is intermittent, meaning at one time it generates a lot of energy, but at some other time it doesn't, because that's the nature of renewable energy generation. Because of this, then we really need a container that we can use to store the energy and to release the energy when we need to utilize it. And if you look at the grid energy, look at the even larger scale, it's also the case. The demand for energy is not a constant throughout the day. During the hours in the middle of the night, there are not much activity. That's why the demand for energy is low. And during these hours, we should store the energies and we release it when the demand are high during the daytime. So batteries are very useful. They are broadly applied to all of these. That's why we have good reason to study battery. Now, so when we study battery, there's a goal, right? We need to achieve some specific properties. We need to improve certain aspect of the battery. And the application actually defines what do we want? What do we want to do with the battery research? So I'm gonna give you a few examples. For example, for the electric cars, what do we want from the electric cars? The number one demand for electric car is that we want to drive for a long distance. So earlier last year, in June 2020, Tesla announced that they are working on this electric vehicle at the 400 miles range. And what does that mean? I did a little Google map search. 400 miles per charge. It allows me to go from San Francisco to Los Angeles in one charge. That's wonderful. You see this map, it shows that the distance is only 389 miles. So this is great. However, I cannot do it via Highway 1 with the beautiful ocean view. This is because the distance is increased. You see that we are never satisfied. We always want to squeeze more energy into the battery. So this is one example. And what else do we want from the car then? Well, some people want the car to drive fast. Some people like fast cars. So I searched on internet, I found this little website, which is very interesting. It's 0 to 60times.com. And apparently there's a whole community of people behind this. They're interested in quantifying precisely how much time does it take for you to accelerate a car from 0 to 60 miles per hour. And you might want to guess which car is the fastest in the world. I cannot hear you, but I guess some people will say Ferrari. Maybe some people will say Lamborghini. Well, whatever you say, you make some people upset. So the real world record is actually held by this electric race car called Grinzo. And that's developed by a group of students in Zurich. So for this car, it can accelerate from 0 to 60 miles per hour in just 1.5 seconds. So that's very impressive. And I want to say that the battery plays a very significant role in this, because the battery's operating voltage is correlated with the accelerating power. So we want the battery to operate at high voltage, and that comes with a whole set of side reactions, undesired degradation, and that's the part of the research goal in this field. And what else about the electric car? Well, we buy a car, we care about the price, right? How much are we really paying for the car, and how much out of it are we paying for the batteries? Apparently, the battery makes up a very significant portion. That's why we need to pay attention to try to reduce the cost. And finally, I would say that the batteries are operated under very different conditions, very harsh conditions. There's cold winter, there's hot summer, and we also want to charge the battery in the very fast speed because we don't want to wait. So we are really purposely abusing the batteries under all these kind of extreme conditions. And all of this sets the challenges for the material, and that's the motivation for our research in this field. So as I said, for battery material, we care about many different aspects of the material, different properties. That's why when we characterize the battery material, we often use this so-called spider web plot to see that a certain material give you different balanced or unbalanced properties in different aspects. You see here, NMC is a very popular cathode material. It shows a very balanced polygon shape. On the other side, these materials on the right-hand side, they have advantage in certain aspects, but they have disadvantages in the other aspect as well. That's why the research in this field is also very active in terms of the candidates, material candidates for the battery application. And people are looking into different materials. People are trying to mix them together. People are trying to design a certain material with target application. So that's our desire. That's what we want from a battery. And what is a battery? Let me show you this schematic cartoon that shows you how a battery operates as you charge and discharge. So the schematics actually is quite simple. You have cathode, you have anode, everything is soaked in the liquid electrolyte. Upon charging and discharging, the lithium ion goes back and forth, swimming through the liquid electrolyte. And the electrons, on the other hand, go through the external circuit. So they are going through different pathways. So to put this cartoon in a more straightforward drawing, I show you this drawing here, schematic here. So upon charging a battery, the lithium ion diffuse from the bulk to the surface of a cathode material. And at the interface, it goes through a little bit of resistance. Once you break through that interface, then the electrons and lithium ion, they go through different pathways, and hopefully they will meet on the other side, on the surface of the anode. And you go through another resistance over the surface, then the lithium ion diffuse from the surface to the bulk on the anode side. Now that reminds me the traveling experience that everybody is very familiar with. And let me do this comparison now. Now, when you go on the trip, maybe to a conference, you have to go through this diffusion resistance, sit in the traffic for so many minutes. Then you get to the airport. you are already very close to the airplane. However, at the interface, there's a little bit of hassle you have to break through. And after that, the passenger and the luggage, they go through different pathways. And usually passengers arrive on the other side with no problem, but the luggage sometimes get missing. If everything goes well, then you pick up the luggage, then you go through another round of this diffusion resistance before you can get to the hotel. So that analogy gives us a little bit of a chemical perspective, understanding of the battery from a chemical perspective, because we talk about the lithium diffusion, we talk about the interface, and all of this has a lot of, let me say, chemical flavor in it. But from the structural perspective, battery is also highly complicated. And before we talk about the details of the battery structure, let's work on our vocabulary a little bit. This word, hierarchy, sorry, I bit my tongue so many times because of this word. And you will see this word many, many times in this presentation. And this is because that's the characteristics of the battery structure. So what is a object with this hierarchical structure? I think we can look it up. We can look at this definition in the dictionary, but it's better that I show you an example. So I made this video. The Earth is highly hierarchically structured. There are so many countries. Inside a country, there are different states. In a state, we can zoom into a certain region of interest. In the Bay Area, there's a nice university. And in this university, you can then focus on this national lab. Inside this national lab, you will see there's a circular shaped synchrotron facility. And next to the facility, if you look through this window over there, you will see me working very hard in my office. So the Earth is a very typical example of a structure with this complexity across different scales. And let me emphasize here that it's the hierarchy that determines the ultimate functionality of this object. And the very same concept applies to battery as well. In the battery, we can look at individual cells. We can then look at these electrodes. We can look at particle assembly. We can look at particles and grain boundaries, even zooming in to a small scale and looking at individual atoms. And there are complexity. There are different challenges associated with different length scales. Let me go through this together with you step by step. So at the cell level, we see that there are many cells with different designs. This cylindrical cell you will find in the electric cars. The pouch cell, on the other hand, is more popular in the battery for cell phones and maybe for laptops. Now, if we look at this cell, you have different electrodes separated by the separator. If we take this cathode, a small piece of cathode, we zoom in, we can look at this cathode with finer details. You will see that this cathode material is made of many, many particles. Each particle is of different size, they have of different shape, they are arranged together in different ways. And these particles, they are embedded in this carbon and binder matrix, collectively forming a highly porous structure. And it's this porous structure that delivers the functionality of energy storage and release on demand. And if we further zoom in, look at individual particle, these particles, they are very small. A typical secondary particle of cathode material is at the scale of 10 microns. Just to give you an idea of the size, I show you the comparison between one single particle at 10 microns versus this cross-section of a human hair. You see that it's very small. But within this small particle, there are structural complexities. You see that in this particle, I show you two examples. On the top, you see this particle internal structure. That's this interconnected, highly complicated crack network There's also isolated voids here and there. Okay, all of this morphological structure has a lot to do with the functionality of this particle. On the bottom, on the other hand, I'm showing you this particularly engineered particle. We engineer the particle such that it looks like onion. You can peel this onion off layer by layer, and these different onion layers, they show you different color because they experience different chemical reactions. Now, if we further look into the subparticle level, looking at the grain boundaries, as you can see in this movie here, we are cutting through this particle and revealing these primary particles. So let me go back and say that these particles, they are called secondary particles because they have internal structures, and they are made of these primary grains, which are assembled together in a fairly closely packed fashion. But each of these primary grain, they have their own characteristics, they have their own orientations, and that adds additional complexity to the battery chemistry as well. Now let's further zoom in and look at the atomic scale. You will see that on this left image, this particular material exhibits this so-called layered structure. You see this white bright dots. They are the atoms of the transition metal cations. And the cyan small dot is the lithium ion. So lithium ion goes in and out as you charge and discharge the battery through this gap between these different transition metal layers. If you slightly zoom out, look at different regions on this same material, however, you will realize that certain area, you still have this layer structure well preserved. But on some other location, you have this layer structure is totally destroyed. And all of this reflects the complexity of this battery material, which has a lot to do with the chemistry and with the functionality of the battery. So I talk about this battery's structural complexity across so many different length scales. And let me also say that the manufacturing of the battery has to go through so many different steps. And within this manufacturing procedure, there are so many things that can potentially go wrong. And that's why it's important to optimize each of these manufacturing steps. Very unfortunately, trial and error is the reality in the optimization process for many of these manufacturing steps. At SLAC, on the other hand, we are conducting the research in this field from a more fundamental perspective. And we are trying to utilize our tools to get more fundamental insights, which will in turn inform the optimization of the industrial procedures. So for this complicated structure, we care about the many different aspects. As I have already said, we care about the arrangement of the atoms. We care about the lattice structure. So we can utilize X-ray diffraction technique to look into this aspect. We care about the charge distribution. We care about the different degree of redox reactions at different locations. So we can look into this aspect using X-ray spectroscopy. And we care about the morphology, which we can utilize X-ray imaging methods. So for all of this, we can find answer at the synchrotron facility. And I'm gonna go through a few examples. As I said, the synchrotron facility generate X-rays with high intensity, which can be utilized for experiments to probing all these different aspects of the material property. And for X-rays, actually, I believe that everybody has more or less some experience with the application of X-rays. So X-rays utilized everywhere. You can see it in the clinical applications. You can see it at the airports. And for industry application, people often use it to look at what's going on inside your cell phone, for example. Now, taking a image using X-ray has very obvious advantage. It offers the highly penetration capability so that you can look through the object without physically taking it apart. It's great. However, let me say that we are not satisfied with this two-dimensional image because all the object we are familiar with in real life is 3D object. When you take a projection image, you effectively flatten it into a two-dimensional space. You get a one image. And why it's important to look at the structure of the material in 3D, I refer to my 10 years old Eric's demonstration. And in this video, you see that Eric made a Lego sculpture, which shows different words in different angles. And if you are only looking at the projection image of this sculpture, the information you get is incomplete. So to get a 3D structure, conventionally, what you would do is you will cut it open. You will physically, open up the object, look inside, and this is exactly what we do in this experiment using focused ion beam and SEM technique. Basically, we use focused ion beam to mill off this particle layer by layer while taking images. Eventually, we can assemble all these images together to form a 3D representation of the object. And this is like giving Eric's Lego sculpture to Evan. My 2-year-old Evan, he's gonna take it apart. He's gonna look at every individual pieces of the Lego sculpture, and he's gonna get a good idea of it. But the problem is that you can imagine this approach will cause some trouble. Some people will be unhappy. That's why with the penetration capability offered by X-rays, we have the opportunity to look at the 3D structure without physically destroying it. And that's the tomography. So what you do in tomography is you collect projection image of the object in different angles. It depends on the sample size. If a cell phone, you might want to rotate the sample. If the target of interest is a patient, you engineer the device so that the device will rotate around the patient. So one way or another, we take projection images of the object in different angles. Eventually, we use a computer software to reconstruct this data set into a 3D matrix. And let me say that this was the Nobel Prize winning technique. It won the Nobel Prize in 1979. And now everybody understands through the Lego demonstration. So now we can take X-ray images of a certain object in 3D with high dimension, high resolution. But let me say that, again, we are not satisfied. And why is that? Because many people don't really get it that the X-ray has colors too. Now, human eyes, our eyes, we are is configured such that we are sensitive to visible light. And you can see from this entire electromagnetic spectrum, the visible light only made up a very narrow band in here. So X-rays, they also have different wavelengths, and if we can somehow probe the material's response as a function of the X-ray wavelength or with X-ray energy, then we can create X-ray colored X-ray image as well. And this is exactly what we can do utilizing a synchrotron facility. So by tuning the X-ray incident X-ray energy on a sample of interest, you can see that the image we take, they shows different contrast, different brightness as a function of the X-ray energy. If you follow the intensity of a certain pixel in an image, you see that it goes up and down. In this energy scan, if we have scanned the energy with a fine step, then we get this spectra. And let me tell you that the shape of this spectra tells us the local chemistry. It tells us what's going on with the element of interest. Is it reduced? Is it oxidized? So with this information, then we can color code our X-ray image. You can see that with single energy X-ray illumination, we get a grayscale image on the left. But with this energy scan, then we can color code the image with the chemical sensitivity. You see that this particle at the pristine state is of nickel 2+ state. As it's being discharged, it's turning green while falling apart. And we can combine this with tomography as well. We can do this in different angles. Eventually, we can create this 3-dimensional representation of the particle with chemical sensitivity. So let me say that when we do experiments like this, we generate a ton of data, and advanced computational tools is very useful in dealing with this. Now we can take colored X-ray image in 3D with high resolution we're still not satisfied. And the reason of this is that in many of the material science study, we want to visualize the material under real operating conditions. We want to see how this material actually evolve, or how does it change as it's doing its job. And I'm showing you some examples here, but let me go back to the topic of battery research. So in this case, we build a battery pouch cell, and we make it compatible with this synchrotron nanoimaging device. And using this setup, then we monitor the evolution of one single particle inside this pouch cell as we operate the cell. And I'm showing you the result here. As you can see, at the very beginning, the entire particle is green. It's at its discharge state. When we charge it in 1 hour, majority of the particle turns red. If we discharge in 1 hour, you see only 50% of the particle return to the green state. And we have the color because we have the chemical spectroscopy fingerprint, which tells you the chemical information. Now, interesting thing about this research is that we then cycle our cell under different rates. This is 10C means a 6-minute charge, and then 6-minute discharge, only 30% of the particle return to the green state. Now, if we slow it down, we do 5-hour charge and 5-hour discharge. And after 10 hours, you see that over 80% of the particle is recovered to the discharge state. Of course, then, if you apply long-term cycling over 20 cycles, you see some difference here. But the major information I'm getting out of this experiment is that these particles, they are very smart. They respond to different externally applied reaction driving force very differently. If we push it really hard, it's going to resist. If we do it slowly, it might cooperate better. So even at single particle level, there's so much of complexity, structural and chemical complexity. Now, if we zoom out to look at the electrode, then, as I said, this electrode is made of millions of particles, and every single particle is unique. Now, with the synchrotron nano imaging technique, we can have a good resolution to resolve every single particles, and we can cover a large field of view so that we have thousands, maybe millions of particles imaged in our scan. Now, once we get the data like this, the first thing we can do is, of course, we can eyeball it, right? For example, in this case, we look at these particles near the top of the electrode, and based on the degree of damage, then we color code it. You see that near the top of the electrode, many particles are pretty severely damaged. That's why they are, color coded to red. Near the bottom of the particle, on the other hand, most of the particles near the bottom of the electrode is more intact, more blue in here. So that actually is very interesting. It tells me that even within this 40 micrometer thick electrode, there's reaction heterogeneity as a function of the depth. The top of the electrode and the bottom of the electrode, they are utilized to different degrees. So that actually becomes a very useful information, which I will mention. How do we utilize this information to improve the electrode? Now, eyeballing the data set like this, just doing it by eye, it's in a way very effective. However, when you have a lot of this data like this, it becomes not possible for you to do this manually. This is because in the electrode, there are so many particles and every one of them are unique. Ideally, we would like to analyze each individual particles one by one. And we have the data to do this, but we just need to develop a tool, a computational approach that can do this in a very effective and efficient way and with very little human intervention. So that reminds me the face recognition. If you take a group photo using your phone. By the way, this is a screenshot recording from my cell phone. If you take this, try to take this group photo, your phone is trying to identify face for you. It identify a face, then put the little yellow box on the face. You see that I was pretty unhappy because my cell phone never recognized Albert Einstein sitting in the very center of this. And you can see that even these very advanced tools, advanced algorithms, they do not give you 100% accuracy. And what do we do then? Now, for our purpose, we also developed a machine learning model which does it for us. So let me show you the comparison here. If you utilize a conventional segmentation tools to analyze the images, it's very likely that the algorithm will distinguish these fragments from the same particle into different particles. This is because they are very severely damaged. These small pieces, they are falling apart. And it makes sense that the conventional algorithm will say that these isolated pieces, they are individual particles. Now, if you take this data set as input for the statistical analysis, then I would say that the result will be off, because you will be concluding that there are so many particles, so many small particles, and each one of them have a very weird shape. In reality, we know that these pieces, they belong to the same particle, and being able to associate these small pieces together as one particle requires a little bit of intelligence. And that's exactly the advanced computational approach can play an important role here. And let me say that it's not like we develop a brand new algorithm that's superior comparing to what you have on your cell phone. It's very difficult. We are not doing that. We are taking what's available in the literature. We make our modification so that it will serve our purpose the best. For example, we have the three-dimensional data. We can look at our three-dimensional data in different angles in computer. And we apply the algorithm to identify the particles as long as they recognize a particle in a few angles. That's all we need to have this particle identified. So with a complicated data set like this, we develop a computing method to identify hundreds, maybe thousands of particles. For each particle length, we can systematically quantify the different characteristics. Every particle has a volume, has a surface area, has its funny shape, has its degree of damage, and then take this data as input. We are building another model to predict the failure. I think to me, the prediction of the failure is not the most critical thing we want to achieve. I think if we are able to predict the mechanical weak point and to predict the failure, then this model can be utilized to help us to determine what kind of property is most critical to the mechanical robustness of the battery electrode. Okay, so I talk about the structural complexity. You see this multi-scale figure again. When I talk about the structural complexity, I went from left to the right. Now let's talk about how do we really utilize the information we learned from our experiments to improve the battery, and we will do this from the right to the left. So at atomic scale, the doping is a very broadly applied method to modify the material property. So in the perfect crystal structure, the atoms, they are aligned in a periodic manner. When we say doping, we are inserting some foreign elements into the system. Now, depends on the property of the dopant and depends on where we put it. We induce different type of distortions to the original lattice structure. And it turns out that in many cases, it's not the material with the perfect structure that gives you the best performance. For example, in here, we see that for lithium cobalt oxide cathode material, we dope it with several different dopants, and we induce this lattice deformation at different locations of the particle. It turns out that this pre-existing lattice deformation actually makes it more robust against the high voltage cycling. As you can see here, the orange line is more stable comparing to the blue line, which is the bare lithium cobalt oxide particle. Now, we zoom out. Remember those grain boundaries. And those grain boundaries are the boundaries between the primary grains, and a lot of damages and side reactions happens at the grain boundaries. And we want to modify the property of the grain boundaries. And the trick here is that we also apply doping to this material, but we dope it with this dopant that has low solubility, meaning that this dopant will spontaneously be pushed out from the lattice structure so that it segregates onto the grain boundary and modifies the property of the grain boundary. So for this material, then you can see that this modified grain boundary has a positive impact on the surface chemistry and also on the mechanical robustness of this particle. Now let's further zoom out to the particle level. And as I said, these particles, they are called secondary particles because they are made of many primary grains. And conventional material has this random orientation of these primary grains. And within each of these primary grains, there's a preferred diffusion direction for the lithium. That's why, because of the random orientation for all these primary particles, the lithium usually has to go through a zigzag before it can reach to the particle surface, and that reduce the efficiency of the lithium diffusion. So on the right-hand side, you see this specifically designed particle with this radially aligned grains, so that you have this, let's call it the ionic highway for the ion diffusion from the core of the particle to the particle surface. So the material on the right-hand side has a much better performance under fast charging conditions. Another example I want to share here is that we also utilize, combine the experimental observation with theoretical modeling to understand the mechanical property of the particles. So from the experiment, in this case, we observe that this particle, solid particle on the left-hand side is more severely damaged. On the other hand, on the right-hand side, you see that this particle with some intrinsic porosity, a hollow particle, is less damaged. So that tells us that there may be a pattern, maybe some intrinsic void space inside the particle will be helpful. So we turn this data to the expert in the theory. With the mechanical modeling, we reveal that some hollow structure indeed can be utilized to mitigate the strain, to release the strain before it accumulates too much and forming the cracks. So that tells us a very interesting thing, because there's a little balance we need to consider here. On the one hand side, we want to have a high density, so we want to pack as much material into the space as possible. On the other hand, if you pack it too much, then it becomes very fragile, easily damaged. So then you can consider to have some building void space in the particle, but you don't want a ping pong ball, because in a ping pong ball you have too much space. You don't have enough material to really do the job, to store the energy and to release the energy. So further zoom out to the electro particle assembly level, I show you here, in this particular case, we are trying to mix particles together, mix particles with different size. The idea here is that the smaller particles will be able to fill in the gaps in between of the larger particles, so that overall you will have a larger packing density. But in order to make this approach effective, we need to understand how these particles self-assemble during the drying process. So we conduct a synchrotron tomography measurement in a dynamic way, so that we can track how this drying process is driving the self-assembling of the particles. You can see that with a optimized drying process, the final product is uniform. You have 130 micron thick electrode on top of the aluminum current collector. Everything is pretty flat. But on the other hand, on the right-hand side, you see that if you did not apply this optimized drying process, the final product has a lot of complexities. It has a rough surface, it has voids, and there's a loose contact. The electrode can detach from current collector, and all of this could be harmful for the performance, for the ultimate performance. So finally, at the cell level, we are also working on this study that's very industry relevant. So we take a cell from our industry partner. So this cell actually, it failed the factory's quality control inspection because of the so-called self-discharging effect. And if you did not catch this. If you build this cell into a battery pack, then you are building in a safety hazard inside this electric vehicle. And we took this cell, we conduct a suite of imaging measurements on this cell. We see that there are all kinds of structural defects across many different length scales. There are impurities, there are different particle packing, delamination, etc., etc. So the idea is that with this observation, then we can go back to our partner and we can tell them that maybe certain certain steps went wrong, and you should pay special attention to different aspects of this manufacturing process. So to summarize, the batteries are very complicated. It has structural complexity across a wide range of length scales. And the manufacturing is also complicated. It goes through many different steps and many things can go wrong. And for the batteries, we want many improvements in many different aspects of the battery performance. And for all of this, we turn to synchrotron facility. We utilize this accelerator facility at SLAC and the other facilities all across the world to look at different aspects of the material so that we can have a rather in-depth understanding. And more importantly, let me highlight here that it's important to bring together people with different expertise. In our research team, we work with the world-leading material scientists, and we utilize the state-of-the-art X-ray techniques, and we utilize a lot of this data science and artificial intelligence approach to get the useful information out of the X-ray data. Eventually, we fit this information into the theoretical modeling. And the theoretical models, they help us understand the fundamental mechanisms. They also help us to inform the design of the materials for our next iterations. So I am very grateful to the collaboration with all of these experts in all different fields. And I also want to take this opportunity to thank Piero, who is my advisor and has been a great mentor for me since I joined SSIL. And with that, I conclude my presentation. And I am gonna go ahead and I'm gonna introduce the discussion panels for today's Q&A session. So we have 3 scientists joining us, Dr. Johanna Nelson-Wecker. She's a staff scientist at SSIL. Johanna did her PhD at Stony Brook in New York. And during her PhD work, she studied biological cells. And after she joined SLAC, she turned to battery cells. Apparently, there are some commonality. So she made a very smooth transition and beautiful work over years. And we have been collaborating over many years already. And we have Dr. Yijin Liu. Yijin was a postdoc at the Berkeley lab, and I know him since his postdoc life at Berkeley. And after that, one day he told me that he decided to go to industry. So that was maybe 3, maybe 4 years ago. Now he's a group leader at the TDK Headway Technologies. And he's leading a group of scientists that's doing advanced material characterization at TDK. And Professor Fan Lin, he's a assistant professor at Virginia Tech. Fan was also a postdoc at Berkeley. I know him a long time ago, since his Berkeley time. And after that, Fan briefly worked for industry. He spent maybe a year, maybe 2 years at QuantumScape, which is a start company that focused on the solid-state battery study in the Bay Area. And Fan later on moved on to work as a professor. And maybe he will tell us what he doesn't like about industry. So with that, we open for the questions from the audience.
Well, Yijin, thank you very, very much. This is a very fascinating talk. Thanks also to the panelists for participating in this. And now we can have questions from the audience. So the way we'd like to do that is at the bottom of your Zoom screen, there is a Q&A If you would type your question into the Q&A, we'll be able to read it, and we'll read it to the panelists, and we'll see what they have to say about it. So let's just begin. There are a number of people who typed questions during the talk, and I'll start with those. So first of all, just an elementary question about the introduction. Has battery storage caught up now with hydropower as a renewable energy? Hydro, of course, it's limited, but it's all night long. How is battery storage doing with respect to that?
Feng, you want to take that one?
Yeah, but I don't have a good number in terms of the cost. My guess would be batteries are still more expensive than the Hydro Pump Pro. The Hydro Pump Pro is taking care of probably over 90% of the storage right now for the entire world, and US also has a lot of it. But in terms of price, my best guess would be the price will be lower than the battery technology. The thing is that the energy round trip efficiency will be lower than the battery technology. For the hydro pump, usually it's about 70 to 80% in terms of the round trip energy efficiency.
Okay, thank you. Yuli asked the following question. The acronym NMC was used to describe electrode material. What does NMC stand for? And actually, there's an extension of that question I'd also like to ask you. The spider plot was very interesting, where you showed that different materials have different characteristics. So what is it about NMC that makes it a good material? And how do you engineer for those different kinds of good properties that you'd like to have?
So NMC is short for lithium, nickel, manganese, or cobalt oxide. This is am I showing the slide?
Yep.
There.
Yes. Okay. So as I said, it's lithium, nickel, cobalt, and manganese oxide, and it's a layer structure, and this is a mixture of 3 different transition metal cations. So NMC is actually a family of materials. There's different compositional configurations. There's, for example, NMC 333, 602, 811, and there's generally a trend that's going for higher nickel content and lower cobalt content. And there's good reason for that, because in NMC, usually nickel is considered to be the major element that's responsible for the redox reaction, which stores and releases energy upon charging and discharging. That's why you want more nickel in the system. And cobalt, on the other hand, is expensive, and there are other issues that we want to reduce and eliminate. Actually, so there's a lot of engineering effort that goes into this, because as you go to higher nickel content, the material becomes less stable. You are exposed to more severe surface damage and other unwanted side reactions as well. That's why there's a general trend, and because of the desire, but there's also a trend of a problem that we are facing as we go to this direction. Actually, let me bring this to Feng again, because he very recently has spending a lot of time, a lot of energy in doing this so-called cobalt-free material, in which you completely eliminate the use of cobalt in NMC. You want to make some comment on this?
So the work that we are doing right now at Virginia Tech is, your cell phone batteries or computer batteries usually use cobalt, because your one of the electrodes is called a cathode. The positive electrode side is utilizing lithium cobalt oxide. The transition metal they use in the lithium cobalt oxide is obviously, by the name, use 100% cobalt. Cobalt is very toxic, high cost, and also cobalt is, you cannot find cobalt in many places on this planet, mostly in Congo Republic. And there are a lot of child labor issues in the country. So not just the cost, not just the natural resource limitation, but also the human rights issue. So everybody's trying to eliminate, or at least reduce the amount of cobalt in the batteries. So the NMC materials, as you can see, that it has the C in the abbreviation, so it still gets cobalt. So the effort right now is to reduce the amount of cobalt, from 10% to 5% and completely remove it. But removing cobalt will cause other problems. For example, if we reduce the use of cobalt and we increase the use of nickel. Nickel is lower cost, at least at this point right now. Nickel is not a bigger concern compared to cobalt. But in the future, nickel might also become a concern. The good thing with the nickel is that it provides much higher energy density because you can perform redox reactions on nickel at a much lower voltage, which means that you don't have to go to very high voltage. You can already get very high capacity. If you want to go higher voltage, you can get much higher energy, but there's always a trade-off between energy and the safety characteristics of batteries. You go higher energy, that could be undermining the safety. So the work we are doing is, push the extreme to increase the nickel content to be very high, and we apply doping chemistry, use other low-cost, earth-abundant elements to dope the material, and without any cobalt, and trying to stabilize lithium nickel oxide-based cathodes.
Okay, thank you. Let's now go to Patrick's question. He wonders, is it possible to monitor the temperature of the microparticles that you observe and correlate this with damage and lifetime?
So monitoring the temperature of a particle inside a functioning cell, to my knowledge, is very challenging. It's number one, you really need a probe that has this high spatial resolution, and also you need to penetrate through whatever is surrounding the particle. And to my knowledge, I don't know. Do any one of you have any?
Is there a big difference between the temperatures of individual particles, or is the temperature kind of uniform through the sample as the battery evolves?
I can answer that one. So the temperature particle to particle is not going to vary that much. You start to have temperature variation issues when you start to have multiple layers of cathode and anode, so multiple layers in the battery. And it depends on the geometry of the battery. Sometimes the batteries are rolled up like a jelly roll, and their temperature can be a big issue. So oftentimes people tend to want to reduce the temperature or allow temperature to be mitigated through the current collector tabs. So basically the positive and the negative terminals are metal and are usually conduct heat very well. So that's a way to cool down batteries.
But let me add that the temperature-dependent behavior of the battery material is a hot topic. So we are not necessarily monitoring one single particle in the system, but in general, if you operate the battery at different temperature, you are looking at different chemistry. So if you go to high temperature, you damage the cell in one way. If you go to low temperature, you induce degradation in a different fashion. So in general, doing this characterization using X-rays and maybe electrons under controlled temperature environment is a very common research interest, and there's a lot of effort in this field.
So in that special cell that you showed us, that you study that at basically all relevant temperatures, and things change, in fact.
For the cells that we have, and the beauty of doing research using X-rays is that it penetrates through the object rather easily. And I show you actually from here. This is not for battery research. One is for synthetic growth, the other one is for catalysis reaction. You can see that we can flow different gas through a sample. We can control the temperature to using this cell to somewhere like 600 degrees C. So that's a pretty wide range, and we can monitor the material's response to the temperature and monitor their behavior under different temperature. And now, if you look at this functional battery in this particular case, we can probably just attach some heater to this holder. And if we are not talking about very high temperature, then it's very doable. There's not much challenge, I would say, in this particular case. Now, on the other hand, I think there's also active research, for example, using electron microscopy to study material under different temperatures, high temperature and low temperature. Maybe Kai-Yang can comment on this a little bit. For example, low temperature, there's cryo-EM applications. High temperature, there are some specific applications as well.
Yeah, I should see the electron microscopy, in situ, especially in situ electron microscopy. The heating is not a problem to add on. So we used to try some. You can heat to very high temperature for the chemical reaction observation. For cryo part, even the conventional microscopy can still do that under like a TM. Very, very, it should be a technical problem. But I think Yijin make a good point is the different temperature range could cause different topics. That's something could relate to the different reaction pathways for the material science students to understand. But from the electron microscopy part, temperature research is always also interesting, I think.
Okay. Jim wanted to ask about the structural and chemical changes over the whole battery lifetime. Do you get enough range that you can really see, like over the whole lifetime, how the battery ages?
So not for this type of operando study, because we have very limited access to the synchrotron beam lines. I mean, for this particular experiment, I was lucky enough to run 20 cycles. I consider that as a heroic experiment. But we do study batteries that's aged, over long-term cycling. And we also, for example, in a very recent work together with a researcher from Bosch, we actually disassembled a cell phone battery that's basically dead, from a very old cell phone. So by looking into those cells and looking into the material characteristics in those cells, and you get some insight into the long-term degradation versus the short-term degradation, which we can easily do in a more direct fashion.
Okay, Jerry has a provocative question for you. He says, I had many portables in my life. It's always the same story. After 4 or 5 years, the battery goes iffy. The same with my iPhone. So why should I trust a battery in a car to last 10 years?
I'll just say that cell phone companies want you to buy a new cell phone every 2 years. Automobile companies realize that you're not going to buy a car every 2 years.
Is there something specific that you do differently for a car battery that's supposed to really last a long time?
No, but I would say that the use case is very different, and so you do tailor the chemistry of the battery for the use case. And the drive cycle of a vehicle is very different than you using your cell phone.
Yeah, I think I will also say that researchers are making improvement in many different aspects. For example, we, as material scientists, we look into the materials. But at the cell level, at a system level, there are researchers who is looking into different protocols for charging a battery. For example, in your iPhone, actually, there's a little option for you. Do you want the iPhone to learn your charging profile, meaning a pattern? So for example, if you have a habit every night at 9 o'clock, you plug in and then you just disconnect in the morning. And if the cell phone knows that, then it could formulate a more a better way to really charge it, instead of charge it at the very beginning, so that your entire cell will be at a high state of charge throughout the night. That's going to be relatively harmful your cell phone. Things like that. The scientists are making improvements in many different aspects, and with all these efforts, the car can probably last for 10 years.
Okay,
So I can,
please.
Then you are muted.
okay, I can add a little bit comment on that. So your cell phones, you most likely you don't turn off your cell phone after you make a phone call, but once you get to a destination, you're gonna power off your car. So your car is not always on 24 hours a day. Your cell phones are on 24 hours a day. So as long as any sort of background programs running in the cell phone, your battery can be discharged. And we also received a comment from one of the Yi Yang actually made a comment that the car batteries are charged to lower voltage compared to cell phone batteries.
Mhm,
So
mhm.
higher voltage will cause some degradation to battery.
Also, the speed at which you charge your battery matters a lot. And so you can fast charge a cell phone battery now, but cars are still requiring much longer to charge, hours to charge, whereas a cell phone battery can charge much quicker.
Paul would like to know, what's the prospect for alkaline metals other than lithium for use in batteries?
Johanna, you want to take that?
Sure. So there's a lot of interest in moving away from lithium-ion batteries to, for example, what we call multivalent ion batteries. And so that would be zinc or calcium or magnesium batteries. Zinc batteries have actually been around for quite a long time, zinc rechargeable batteries, but they can't compete right now with capacity with lithium-ion batteries.
Okay. Steve would like to know how many of the discoveries that have been described in this talk have actually made it into production in useful batteries. Maybe what's that cycle to get this information into realistic production?
Well, it depends on how you define this. I mean, from our perspective, as SLAC, we do research from the fundamental side, but we do get information that's very much relevant. And I have shown you some examples. For example, for the electrode, we see different degree of damage at the top and the bottom of the electrode. Do I have it here? Yes, I have it here. So you see that in the imaging experiment, we see that the top and the bottom of the electrode, they are utilized to different degree, so that they have different degree of damages. So one of the follow-up of the work for this particular study is that we can then make the electrode out of multi-layer different materials. So at the top, you can use some material that's more robust mechanically, but other aspect of the performance can be relatively low. And on the bottom, you can swap. So actually, with this input, with this observation, is guiding the design of the electrode. And there are experimental efforts that's following up. And I don't know how far it will go, how long it will take into the real factory production, but it's certainly making its impact.
Okay, Kaiyang, do you have anything to say about this question?
I don't have too much to comment on this one. Maybe I have something to say about next one. I'm looking at those questions.
Okay. Well, there is a question about what materials and technologies are most advantageous for battery recycling at the end of life? So is there a way to compromise between recyclable materials and materials that have excellent energy density and properties?
Ben, you want to comment or you want me to comment? You are muted.
And you're muted.
Anyhow.
You go
Yeah.
first. You go first.
Okay, I go first. Okay, so apparently the recycling of the battery material is a very important topic. There are many different ways of doing this. And recently we have some study where we simply apply some annealing process to the used battery electrode. And what we observed is that if you control the condition just right, you can reactivate a lot of the lost capacity. And but there, I mean, from my perspective, there are also balance you need to consider. For example, if you really apply very high temperature to melt down everything, then you just you can harvest those elements, but the cost is also very high. So you don't want to do that. And if you how do you optimize the process so that it's getting you what you want, but in a cost-effective, cost-efficient way? I think that requires a lot of effort. That's what I have. Thank.
Yeah, I think Yijin covers the most part of the recycling. There are a lot of research programs funded under Department of Energy on the battery recycling, because it's really recognized as an important topic these days. And not just recycling of batteries, it's essentially recycling and upcycling of everything. It's just becoming way much more important today than it used to be. In terms of the materials selection, you can certainly tune what you want to use for making the battery, and you want to get materials from earth abundant resources. That's part of what we do as well to get rid of cobalt in our batteries, and eventually we're going to get rid of nickel as well to use even more earth abundant elements such as iron, but still with high energy density, and that's very, very challenging. So getting materials into batteries that are more recyclable than what we have today, at least for now, I think we will have to compromise and sacrifice the energy density a little bit. But that's always a thing that within the mind of every battery researcher is to make it more sustainable.
Okay, we're coming to the end of the question, so let me make this the last one, but it's pretty open-ended. What will battery technology look like 10 years from now? And maybe even further in the future, 20 years from now? Where are we going? Do you have a vision for that? Actually, I'd like to hear from all of you.
So I have some ideas about this. So, TDK Corporation is kind of also leading in one market of the battery. So we actually announced the all ceramic rechargeable battery, solid state battery years ago. So that's one actually advanced technology people are quite interested about and excited about now. So if you look at the people's expectations and market, the market expectations, the battery industry is still very promising, and people are looking for the new materials, the new configurations of the batteries. I should see in 10 years, 20 years, it's going to be a hot market, hot area for research, definitely. But different technologies will pop up to have their advantages and disadvantages. That's why this talk is about how those materials can be studied by using SLAC facilities and also many advanced material analysis methods. So in that way, no matter how the technology develop, they need those facilities, the technologies to understand how the material work, how the batteries work, how the chemical reactions happen, and how the structures change, evolve during the battery cycling. So I should see, I will see more development, more advancement of technology in the near future, just in the near future. But it'll be a little bit difficult. You see, it's very complicated for the research of the material science, material chemistry. That's my point.
I can go next.
Please.
So I would say that I think what the trend we're seeing right now is in the early 2000s, battery manufacturing was really driven by cell phones and laptops, and cars sort of just took the batteries from laptops and stuck them in cars. But I'd say in the last 10 years now, really the automobile industry is driving battery research for vehicles. And so I would think that in the next 10, 20 years, we're going to see even more diversity in the types of batteries and the chemistries in batteries, depending on their use cases. So if it's going to go in a vehicle that's a truck, it's going to have a very different battery than the battery for a personal vehicle, or even a fleet vehicle is going to look different than a personal vehicle. And we're also going to see batteries in airplanes. So electric airplanes, at least for short distances, maybe helicopters, not airplanes, I'm not sure. And then those batteries are also very different than the batteries that are going to be replacing our grid. So for grid storage, you don't really care about anything except very, very cheap energy.
Yes, maybe let me echo that. I think in the next 10, 20 years, it's not like a single technique or single application driven the research activities. It's more like an ecosystem where you have all these application scenario which requires different performance, emphasize on different aspects of the performance. Exactly what we are showing on a spider web plot. So, going back to the battery recycling topic, for example, a battery pack retired from an electric vehicle can potentially be utilized, with very minimal treatment for a different application. So building up this entire ecosystem, then, treat it as a whole, and then potentially we can really tackle this entire problem in the most effective way.
I think I think the comments made by Yijin, Kai-Yang, and Johanna are all excellent. But I want to say to everybody that let's be patient. You're asking a question within 10 years and 20 years. It took about 25 years, more than 25 years, I believe, to really make the batteries, lithium-ion batteries, widely available for consumer electronics. And it will take much longer, potentially, to enable batteries for applications such as airplanes. Because for now, across the board, based on the theoretical calculation, it's still very difficult to identify a battery chemistry that can work for a long-distance airplane. Drones and helicopters, like what Johanna said, will be likely in the near term. The future will be a mix of different battery chemistries. Different applications will be using different type of technologies. For example, large-scale renewable energy storage, you probably are not going to use very expensive lithium-ion batteries, and the alternative technologies could be flow batteries, which occupies larger volume. But who cares in the middle of nowhere when you generate renewable energy? You have a lot of space. You can also use sodium-ion batteries, which is presumably more renewable, more sustainable than lithium chemistry. So there are all these opportunities for research and for technology development over the next, instead of saying 10, 20 years, let's say 50 years.
Okay, well, this has been a really fascinating discussion. Thanks to Yijin, thanks to all of the panelists. Thanks to you, the audience, for sticking with it. Let me just make a couple announcements. First of all, if your friends might benefit from this, but they missed it, we record all these public lectures and put them up on the SLAC YouTube channel. So probably in about a week, the film of this lecture will be there, and all the other public lectures that we've had in the past. And please take advantage of that. It's a very nice resource. These public lectures take place about once every 2 months. The next one will be at the end of March, and it'll go all the way to the other end of what SLAC does. It'll be about particle physics. So if you're interested in that, as well as batteries, please come to that. If you'd like to get on the mailing list, so that you get the announcements of these public lectures, please go to the SLAC website. And if you look for public lectures, there's a place there to sign up for our mailing list. And we look forward to seeing all of you, as I say, about the end of March for the next one of these and for more of them in the future. So thank you all very much, and we'll see you soon. Bye-bye.
Thank you.